An invisible force is tearing our universe apart. This mysterious power, known as dark energy, dictates the ultimate fate of everything we see, yet it slips through our most advanced detectors completely unseen. The story begins with a Nobel Prize-winning shock, the discovery that the cosmos is not merely growing, but its expansion is accelerating at a breakneck pace. By the end of this journey, you will understand the compelling evidence for this cosmic phantom and the startling theories about what it could be. We will explore how a single number holds the key to whether our universe faces a frozen emptiness or a violent end. What does it feel like to live in a cosmos dominated by a force you can never touch? Albert Einstein once scribbled a number into his equations, a number he would later call his greatest blunder. The year was 1917, and his theory of general relativity had just reshaped our understanding of gravity and space. Yet the equations predicted a universe in motion, either expanding or contracting. This deeply troubled Einstein. The prevailing wisdom of the time, supported by astronomers' observations, insisted the cosmos was eternal and static. A universe in flux seemed philosophically unacceptable, so Einstein introduced a mathematical fix, a repulsive force woven into the fabric of spacetime itself. He called it the cosmological constant. Its sole purpose was to hold the universe still, to perfectly balance the inward pull of gravity and keep everything forever in place. It was a fudge factor, an admission that even the greatest minds can be swayed by the desire for a comfortable, unchanging reality. When evidence for an expanding universe emerged just over a decade later, Einstein readily discarded his constant, dismissing it as a theoretical misstep. The chapter appeared closed. The cosmological constant was relegated to a footnote in the history of physics, a cautionary tale about forcing nature to conform to human expectations. But the universe had a surprise in store. That abandoned idea, that so-called mistake, was not a dead end. It was a seed lying dormant for decades, waiting for the right moment to sprout into a truth far stranger than anyone could have imagined. For decades, the cosmic story seemed straightforward. A giant explosion flung everything outward, and ever since, the collective gravity of all the galaxies has been steadily applying the brakes. The great question was simply how much mass existed, and whether that gravity would one day pull everything back together in a big crunch, or if the universe would just coast onward, expanding forever at an ever-slowing rate. Then, in the late 1990s, two rival teams set out to measure this cosmic deceleration using the universe's most reliable mile markers, Type 1, a supernova. Imagine a particular kind of stellar explosion so uniform and so brilliant, it can be seen from billions of light years away. Astronomers call these standard candles. By observing how bright these explosions appear from Earth, scientists can calculate their true distance with incredible precision. It is like knowing the exact wattage of a light bulb. If it looks dim, you know it is far away. Both teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were painstakingly cataloging these distant beacons. They were searching for a subtle change in the expansion speed over cosmic time, expecting to confirm the universe was slowing down. Instead, they found a ghost in the data. The most distant supernova were significantly dimmer than their models predicted. This was not a small error. It was a monumental discrepancy. A dimmer supernova meant it was much, much farther away than anyone had thought possible. The only explanation was that the space between us and that ancient explosion had stretched more than anyone had anticipated. The universe was not just expanding, it was accelerating. The collective disbelief that swept through the teams was palpable. They checked and rechecked their data for errors. They scrutinized their instruments and their methods, searching for any possible flaw. Could interstellar dust be dimming the light? Had they misidentified the type of supernova? Every alternative was exhausted, and the result remained. The cosmos was flying apart faster and faster, as if pushed by an invisible hand. This discovery was so profound, so contrary to everything we thought we knew, that it earned the teams the Nobel Prize in Physics in 2011. Decades of cosmological dogma were overturned in an instant. The hunt for the identity of this mysterious force, this phantom in the equations, was now officially on. So the phantom had a name and a face, one that was hauntingly familiar. The most straightforward explanation for the accelerating cosmos is a ghost from the past, Einstein's own cosmological constant. This idea suggests that dark energy is not some substance flowing through space, but a fundamental property of space itself. Think of the vacuum of empty space not as a true nothing, but as a seething, bubbling sea of potential energy. This energy density, represented by the Greek letter lambda, is constant. Every cubic centimeter of space, whether here on Earth or in the vast emptiness between galaxies, contains the exact same tiny amount of this repulsive force. Now, here is the crucial part. As the universe expands, it creates more space. And if every new bit of space comes with its own built-in dose of repulsive energy, the total push driving the expansion grows. Gravity, which weakens as galaxies move apart, is quickly overwhelmed. The acceleration does not just continue, it intensifies, exactly as the supernova data revealed. The mathematics behind this are beautifully simple. A single number in Einstein's equations that perfectly describes the observed cosmic speed-up. It is an elegant, almost poetic solution, a cosmic apology to its creator. Yet this elegant answer casts a very long, very dark shadow. When physicists turn to their other great theory, quantum mechanics, to calculate what this vacuum energy should be, the result is not just a little off. It is catastrophically wrong. The predicted energy density is a number so unimaginably large, it would have torn every atom in the universe apart in a fraction of a second after the Big Bang. To match what we actually observe, the theoretical prediction must be wrong by a factor of 1 followed by 120 zeros. This is not a small rounding error. It is the most severe discrepancy between theory and observation in the entire history of science. The cosmological constant, for all its explanatory power, sits atop a foundation that is completely unknown to us. We have a number that works, but we have no idea why it has the value it does. This is the cosmological constant problem, a glaring reminder that our understanding of the universe's most basic fabric is still profoundly incomplete. But what if the phantom is not a ghost but a chameleon? This is the compelling possibility offered by Quintessence, a theory that reimagines dark energy not as a static number, but as a dynamic, evolving force field pervading all of space. The name itself is a deliberate echo of an ancient idea, the fifth element or essence that Aristotle believed filled the cosmos beyond Earth. In modern physics, Quintessence proposes a fifth fundamental force, a field whose strength and energy density are not locked in place like Einstein's cosmological constant, but can change over billions of years. Imagine the difference between a single, unwavering note held for all eternity and a complex, evolving symphony. The cosmological constant is that single note. Quintessence is the symphony, its energy ebbing and flowing with the age of the universe. This dynamism offers a natural explanation for one of the great puzzles of cosmic acceleration. Why did it only begin to dominate the cosmos a few billion years ago? If dark energy is a constant, then its repulsive push has always been there, but it was simply overwhelmed by gravity when the universe was younger and denser. Quintessence, however, can be designed to have been weak and dormant in the early universe, only awakening to its full repulsive power in more recent cosmic times, neatly matching our observations. The mechanism behind this strange force hinges on a special type of field known as a scalar field. You can think of it as an invisible fluid filling every point in space with a certain potential energy. When this field sits high on its energy slope, it exerts a powerful negative pressure, a kind of gravitational repulsion that stretches the fabric of spacetime itself. This is the repulsive gravity effect. As the universe expands, the field can slowly roll down its potential energy hill, changing its properties and thus changing the strength of dark energy over time. This is where the ultimate fate of the cosmos gets truly fascinating. The specific shape of this energy landscape dictates our future. In some quintessence models, the field gently rolls to a stop, causing the acceleration to gradually slow, allowing gravity to reassert a more gentle control. In other, more extreme scenarios, the field races down its slope, its repulsive power growing infinitely stronger. This could lead to a truly terrifying end known as the Big Rip. In this scenario, the accelerating expansion doesn't just push galaxies apart. First, it would tear galaxy clusters apart. Then, it would rip individual galaxies to shreds. As the acceleration grows unchecked, it would overcome the gravity holding stars together, then the forces binding planets, and finally, just moments before the end, the very atoms that make up all matter would be violently torn asunder. The entire universe would be reduced to a thin, cold mist of isolated particles, forever flying apart into an absolute and final emptiness. This range of possibilities, from a gentle slowdown to a catastrophic rip, is what makes quintessence so compelling to theorists. Unlike the single, fixed prediction of the cosmological constant, quintessence offers a spectrum of testable futures. By measuring the expansion rate with ever greater precision, astronomers are not just looking back in time, they are reading the first few lines of our cosmos's final chapter, searching for any hint that the phantom force is changing its strength. The hunt is on to see if dark energy is a simple, eternal constant, or a dynamic and exotic field whose story is still being written. At the heart of this cosmic mystery lies a single critical number. Cosmologists call it the equation of state parameter, a value represented by the simple letter W. This is not just another abstract symbol. It is the key that could unlock the true identity of dark energy, telling us whether it is Einstein's simple constant or a dynamic, changing field. The parameter W describes the relationship between the pressure and the energy density of this mysterious component. Think of it as a cosmic fingerprint, a unique signature that defines how a substance pushes or pulls on the fabric of space. For ordinary matter, this value is 0, meaning it exerts no pressure and gravity pulls everything together. For radiation, W is positive 1/3, contributing an outward push. But for dark energy, the value is profoundly strange. It is negative. A more negative W means a stronger, more repulsive pressure. If dark energy is indeed Einstein's cosmological constant, a simple property of empty space itself, then W must be exactly -1. It is a fixed point, an unwavering value written into the laws of physics. This is the simplest and most elegant answer. Yet if dark energy is a quintessence field, a cosmic chameleon, then W could be different. It might be greater than -1, perhaps -0.9, indicating a force that is slowly weakening over time. or, in the most dramatic and terrifying scenarios, it could be less than -1, say -1.1. This would signal a phantom energy, a force whose repulsive power grows infinitely stronger, dooming the universe to that ultimate big rip. So how do we measure this elusive number? Astronomers are not looking through a single telescope. They are building a cosmic case by combining multiple, independent lines of evidence. They use distant supernovae as standard candles, just as the original teams did, but with far greater precision. They study the faint afterglow of the Big Bang, the cosmic microwave background, which holds a frozen imprint of the universe's early composition and expansion rate. And they employ a remarkable tool called Barion acoustic oscillations. This method uses the large-scale structure of the universe itself as a cosmic ruler. In the early cosmos, sound waves traveled through the hot plasma, creating ripples of slightly denser matter. These ripples froze in place when the universe cooled, leaving a preferred distance between galaxies. By measuring this standard distance at different epochs, scientists can track how the expansion rate has changed over billions of years. Each of these methods, supernova, the cosmic microwave background, and Barion acoustic oscillations, gives them a different slice of the cosmic history. When combined, they allow researchers to triangulate the value of W with breathtaking accuracy. Every new observation, every more precise measurement, is a step toward answering the ultimate question. Is W exactly -1, or is it something else? A confirmed deviation, even by a tiny fraction, would be a scientific earthquake. It would shatter the elegant simplicity of the cosmological constant and force us to accept that dark energy is something far more complex and dynamic than a simple number in an equation. The quest to measure W is one of the greatest detective stories in modern science, a painstaking search for a single digit that holds the final chapter of our universe in its grasp. Think of a stellar time bomb, a white dwarf star stealing matter from a nearby companion. It greedily pulls in gas until it reaches a very specific critical mass. At that instant, the entire star is consumed in a thermonuclear fire, a titanic explosion so bright it can outshine an entire galaxy. This is a Type 1, a supernova. Its brilliance is not random, because the trigger is always that exact same mass. The peak brightness of the explosion is incredibly uniform. Every single one of these events, anywhere in the universe, reaches roughly the same intrinsic luminosity. This makes them the gold standard for cosmic cartography, a perfect standard candle. If you know how bright the light bulb truly is, you can tell exactly how far away it is by how dim it appears. But astronomers go a step further. They do not just look at the peak brightness. They study the entire light curve, the way the supernova brightens and then fades over weeks and months. The precise shape of this curve allows them to make fine adjustments to standardize the candle even further. It is a painstaking process of calibration and correction, accounting for interstellar dust that can redden and dim the light, and for subtle variations in the explosion itself. This meticulous work transforms these stellar blasts into the most precise mile markers in the universe. Now, rewind to the 1990s. The two research teams were using these mile markers to measure cosmic deceleration. They looked deep into space and therefore far back in time, observing supernova that exploded when the universe was much younger. They expected these ancient beacons to appear slightly brighter than the simple expansion model predicted, because the universe's expansion should have been faster in the past, placing the supernova a little closer. Instead, they found the opposite. The most distant supernova were about 25% dimmer than anyone had anticipated. A dimmer standard candle can only mean one thing. It is farther away, much, much farther. The only way to explain these observations was if the space between us and those ancient explosions had stretched more than anyone thought possible. The universe in its youth was not expanding at a slower, braked pace. It was expanding more slowly than it is today. The acceleration was real. These dying stars, these fleeting flashes of light from billions of years ago, were the definitive beacons that illuminated the invisible force tearing the cosmos apart. They provided the first direct, undeniable evidence that something was profoundly wrong with our understanding of gravity and the cosmos. The phantom had left its first clear footprint. While the supernova revealed the acceleration directly, a second, completely independent line of evidence was waiting in the cold depths of space, an ancient echo from the very beginning of time. This is the cosmic microwave background, the faint afterglow of the Big Bang itself. Imagine the entire universe filled with a uniform, dim glow, a relic of a time when the cosmos was a seething, opaque plasma, just 380,000 years old. As the universe expanded and cooled, this hot light stretched into the microwave part of the spectrum, and it now permeates all of space, a fossil from creation. This background is not perfectly smooth. Satellites like Planck have created exquisitely detailed maps, revealing it as a mottled canvas of tiny temperature variations, hotter and colder spots that differ by mere millionths of a degree. These minute ripples are a baby picture of the universe, a snapshot of the density fluctuations that would one day seed every galaxy, star, and planet. The specific pattern of these spots, what cosmologists call the power spectrum, acts as a cosmic barcode. The spacing and height of the peaks in this graph encode fundamental information about the universe's composition, geometry, and ultimate fate. One of the most critical revelations from this barcode is the geometry of the cosmos. The data shows with overwhelming certainty that the universe is geometrically flat. In a flat universe, parallel lines never meet, and the angles of a triangle always add up to 180 degrees. This flatness is not an accident. It requires the total density of matter and energy in the cosmos to be at a very specific critical value. When astronomers add up all the matter they can account for, both the ordinary atoms we are made of and the invisible dark matter that binds galaxies, it only amounts to about 30% of this critical density. The universe is flat, but 70% of the required stuff is missing. The only component that can fill this vast 70% void is a form of energy with a strong negative pressure, a repulsive force that perfectly accounts for the missing density. Dark energy is not just a suggestion from distant supernova. It is a mandatory ingredient written into the very first light of the universe. The precise positions of the peaks in the cosmic microwave background's power spectrum point directly to the existence and the exact amount of this mysterious component. It is the universe's own birth certificate, and it lists dark energy as a majority shareholder in our cosmic destiny. This ancient whisper from the dawn of time powerfully corroborates the story told by the dying stars, confirming that the phantom force is real, pervasive, and fundamentally shapes the fabric of our reality. A third, completely independent witness steps forward, its evidence etched not in dying starlight or ancient radiation, but in the very architecture of the cosmos. This method relies on the ghostly echo of primordial sound waves frozen in time, a phenomenon known as Barion acoustic oscillations. To understand this, you must travel back to the universe's first 400,000 years. It was a seething, opaque soup of particles and light, a dense plasma where photons and matter were locked in a constant tug of war. In this hot, pressurized fluid, gravity would try to pull matter inward, creating an overdense region. But the intense radiation pressure from the trapped photons would push back, creating a powerful outward shock wave. This created a spherical sound wave, a ripple of compressed matter and energy that expanded outwards from the initial density fluctuation at over half the speed of light. This cosmic drumbeat continued for millennia until the universe cooled just enough for atoms to form. At that moment, the photons suddenly broke free and the plasma vanished. The sound waves instantly froze in place, their expansion halted forever. They left behind a telltale signature, a spherical shell of slightly denser matter with a very specific radius. That radius, the distance the sound wave could travel before the music stopped, is our standard ruler. It measures about 500 million light-years across. This means that if you could look at the universe on the largest scales, you would find that galaxies have a slight statistical preference to be separated by this specific distance. It is as if the cosmos is imprinted with a faint grid, a fossilized echo of its own fiery infancy. Projects like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, painstakingly reconstructing this three-dimensional cosmic web. By measuring the apparent size of this standard ruler at different distances, and therefore at different eras in cosmic history, astronomers can track how the expansion of space has stretched the ruler over billions of years. The results are unequivocal. The scale of these Barion acoustic oscillations confirms that the expansion of the universe began to accelerate around 5 billion years ago. It is a robust, clean measurement that is less vulnerable to the interstellar dust and calibration uncertainties that can plague supernova studies. Here, the evidence is not a distant explosion or a faint glow, but the grand pattern of cosmic structure itself. The phantom's signature is written in the positions of the galaxies, a final, undeniable confirmation that an invisible force is guiding the destiny of everything we see. So after combining all the evidence, we are left with a cosmic recipe that is both staggering and deeply humbling. The universe we thought we knew is just a thin shimmer on the surface of a vast, dark sea. The consensus pie chart of the cosmos breaks down like this. A mere 5% of the entire universe is made of the ordinary atomic matter that forms every star, every planet, and every one of us. This is everything we can see, touch, and study directly. It is the entire periodic table, and it is a cosmic afterthought. The remaining 95% is invisible and unknown. 27% is dark matter, the mysterious gravitational glue that binds galaxies and clusters together, yet refuses to interact with light. And the overwhelming majority, a full 68%, is the phantom itself, dark energy, the repulsive force accelerating the expansion of space. Let that sink in. The very stuff of our being, the atoms forged in the hearts of stars, constitutes a mere 5% of the cosmos. We are not even made of the universe's primary ingredients. We are a rare and exotic contaminant in a cosmos dominated by shadows. This new cosmic recipe does more than just redefine the contents of the universe. It fundamentally reframes our place within it. The Copernican revolution taught us we are not the geographic center of the cosmos. Now, modern cosmology tells us we are not even its material center. The fundamental nature of 95% of reality is a complete and total mystery to us. This is the great challenge of our century. For all our knowledge, for all our technology, we are still just beginning to decipher the true composition of the world around us, a world made mostly of phantoms. This staggering mismatch points us toward the quantum vacuum, a realm where nothing is truly nothing. To grasp why Einstein's cosmological constant creates such a profound puzzle, you must abandon the idea of empty space as a true void. According to quantum mechanics, the vacuum is a seething, chaotic foam. At the tiniest imaginable scales, pairs of virtual particles and antiparticles spontaneously flicker into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This endless dance of creation and destruction is not just theoretical. We can observe its effects, such as tiny shifts in the energy levels of atoms, proving this quantum activity is real. All this frantic activity means that every single cubic centimeter of empty space, the vacuum itself, possesses a baseline energy. Physicists call this zero-point energy, the irreducible hum of the universe. It seems like the perfect candidate for dark energy, a built-in repulsive force inherent to space itself. But here lies the catastrophe. When physicists attempt to calculate how much energy this quantum frenzy should contribute, the result is not just a little high. It is catastrophically, unimaginably immense. The theoretical prediction for the vacuum energy density overshoots the observed value of dark energy by a factor of 1 with 120 zeros after it. This is not merely the worst prediction in the history of physics. It is a screaming paradox. The vacuum energy calculated from quantum theory should be so powerfully repulsive that it would have blown the universe apart in the first fraction of a second of its existence. Stars, planets, and atoms could never have formed. The fact that we exist to ponder this at all means our understanding is fundamentally broken somewhere. This colossal mismatch, known as the cosmological constant problem, is a glaring signpost pointing toward a deeper truth. It suggests that our two most successful theories, quantum mechanics and general relativity, are somehow incompatible when describing the fabric of space itself. We are likely missing the final piece, a theory of quantum gravity that can seamlessly unite the very large with the very small. The vacuum itself may hold the secret to dark energy, but our current mathematics cannot yet decipher its true, quiet nature. This concept of gravitational repulsion feels like a direct violation of intuition. We are taught from birth that gravity pulls things together, never pushes them apart. Yet Einstein's theory of general relativity contains a subtle and profound twist, one that allows for exactly this kind of behavior. Gravity, in Einstein's universe, is not just about mass. It is about the combined effect of mass, energy, and even pressure. For all the matter and energy we encounter in daily life, from a planet to a beam of light, the pressure component is either positive or so negligible that its gravitational contribution is an attractive pull. This is why apples fall and planets orbit. Dark energy is different because it possesses a property so extreme it flips gravity's script, a powerful negative pressure. Think of a stretched rubber band. It is taut, filled with potential energy, and it wants to snap back to a relaxed state. That inward tension, that desire to contract, is a form of negative pressure. Now, imagine that same kind of tension is an intrinsic property of the vacuum of space itself. Every tiny volume of nothingness is like a hyper-stretched band, storing energy and wanting to pull inward. According to general relativity, this intense negative pressure does not just pull on itself. It generates a gravitational field that is repulsive. The more space there is, the more of this stretched fabric exists, and the greater the collective push becomes. This is the bizarre mechanics behind the accelerating universe. Dark energy is not an external force shoving galaxies away. It is a property of spacetime itself, and its own peculiar gravitational influence is causing the cosmos to push itself apart at an ever-increasing rate. It is a cosmic recoil effect, written into the geometry of reality by Einstein over a century ago, waiting for its moment to be discovered. This cosmic tug of war between matter and dark energy has not been constant. For billions of years, gravity was in complete control. In the dense, youthful universe, every galaxy and every particle of dark matter was close enough to exert a powerful gravitational pull on everything else. Think of the entire cosmos as a ball thrown directly upward. For a long time, it slows down, its ascent braked by the relentless pull of Earth's gravity. The early universe was that ball, its expansion steadily decelerating under the collective weight of all its matter. But then, something changed. As space continued to stretch, the matter within it was diluted. The density of both normal and dark matter dropped, weakening gravity's grip with every passing eon. Dark energy, if it is indeed a cosmological constant, played a very different game. Its energy density did not drop. Every new cubic light-year of space that came into existence carried with it the same tiny, repulsive kick. The scales were tipping. The braking effect of gravity was fading, while the persistent push of dark energy held its ground. Then, roughly 5 billion years ago, a silent, universe-altering crossover occurred. The repulsive effect of dark energy finally surpassed the attractive pull of matter. The cosmic expansion did not just stop slowing down, it began to speed up. Our universe transitioned from a matter-dominated era to a dark energy-dominated era. This recent shift in power is why the accelerating expansion feels like a new development in the cosmic story. For 9 billion years, gravity ruled. For the last 5 billion years, a phantom has been in charge, subtly guiding the universe toward a future we are only just beginning to understand. The phantom leaves no direct image, but it betrays its presence by bending the very fabric of reality. To map this invisible architect, astronomers deploy a technique as subtle as the force itself, a phenomenon called weak gravitational lensing. Imagine staring at a distant galaxy through a vast, lumpy pane of glass. The glass is the combined gravitational field of all matter, both light and dark, between you and that galaxy. As the galaxy's light travels toward us for billions of years, its path is gently warped and twisted by these invisible lumps of mass. The result is not a dramatic funhouse mirror distortion, but a slight, systematic shearing. The images of millions of background galaxies are stretched and aligned in a coherent pattern, like leaves floating on a gently flowing river. By meticulously measuring these tiny, percent-level distortions across the sky, scientists can reconstruct a three-dimensional map of the total mass distribution, revealing the hidden cosmic scaffolding of dark matter. This mass map is crucial because it shows us how the cosmic web, the great filamentary structure of the universe, has grown over time, and the growth of this web is in a direct tug of war with dark energy. The repulsive push of dark energy works against gravity's tendency to pull matter together into clusters and filaments. By comparing the lensing map from different cosmic epochs, astronomers can measure the strength of dark energy's grip and how it has been slowing the growth of structure for billions of years. Another powerful, yet conceptually simple, tool is the clustering of galaxies. Galaxies are not scattered randomly through space. They trace out a vast cosmic web, gathering into immense clusters, long filaments, and enormous empty voids. The precise statistical pattern of this clustering, how likely you are to find two galaxies at a certain separation, acts as a fossil record of the universe's expansion history. Dark energy, by controlling how fast the universe expands, directly imprints itself on this pattern. The size of the voids and the tightness of the clusters we see today tell a story about the force that has been shaping them. To harness these subtle signals, scientists have launched monumental projects like the Dark Energy Survey, which used a powerful telescope in Chile to map hundreds of millions of galaxies and measure the shapes of tens of millions. Its data has already provided some of the most stringent constraints on dark energy's properties, but this is only the beginning. The upcoming Vera C. Rubin Observatory, with its colossal 3.2 billion pixel camera, will undertake the most ambitious astronomical movie ever made. Over 10 years, it will scan the entire southern sky every few nights, creating an unprecedented, deep, wide, and dynamic map of the cosmos. It will detect billions of galaxies and measure weak lensing and clustering with a precision that was once the stuff of dreams. We are no longer just looking at the universe. We are learning to watch it breathe, to see the subtle ways the invisible hand of dark energy molds the largest structures in existence. Each distorted galaxy, each vast empty void, is another data point, another brushstroke in a shadow portrait of the phantom that holds our fate. Among these cosmic destinies, the most probable end is also the most silent. If dark energy is indeed Einstein's simple constant, an unwavering force with a value of W equals -1, then the universe is set on an irreversible course toward the Big Freeze. This is not a dramatic explosion or a violent collapse, but a slow, inexorable fading. Picture our cosmic neighborhood, the local group of galaxies bound together by gravity, as a single, isolated island. For now, we remain connected, but every other galaxy cluster beyond our own is already drifting away from us, their light stretched into invisibility as the space between us expands faster than light can traverse it. One by one, they will vanish over the cosmic horizon, their stories forever lost to us. The universe will seem to shrink, even as it grows immeasurably vast, until our island is the only thing left visible in an infinite black ocean. Within this dwindling archipelago, the fuel for new stars will slowly run out. The great clouds of gas and dust that coalesce into stellar nurseries will be torn apart by the accelerating expansion, scattered into an ever more dilute haze. The last star will flicker into existence, burn for billions of years, and then go out. One by one, the lights will vanish. The cosmos will enter its final age, a dark era populated only by the corpses of stars, black holes, and frozen planets. Temperature relies on the movement of particles, on the transfer of energy. But in this vastly stretched emptiness, particles will be so far apart they will almost never interact. The universe will approach absolute zero, the point where all molecular motion ceases. This is the heat death, the ultimate triumph of entropy, where energy is uniformly distributed and no work can ever be done again. It is a quiet, cold, and profoundly lonely conclusion, a whisper that fades into an eternal silence. Yet the Big Freeze is not the only possible finale. The phantom could awaken to a far more violent and dramatic end, a cosmic apocalypse known as the Big Rip. This scenario unfolds if dark energy is not a gentle constant but a vicious phantom energy, a force with an equation of state where the value of W is less than -1. In this terrifying model, the energy density of dark energy does not remain steady. It actively grows stronger as the universe expands. The acceleration would no longer be a steady push but a super exponential surge, a runaway feedback loop of repulsive gravity. The timeline of this unraveling is both precise and horrifying. Billions of years before the final moment, the mounting repulsion would overcome the gravitational glue holding the largest structures together. Galaxy clusters, those immense families of thousands of galaxies, would be the first to be torn asunder, their members flung into the ever-widening void. As the end draws closer, the phantom's grip tightens. About 60 million years before the terminus, the force would be strong enough to shred our own Milky Way galaxy, pulling stars away from each other in a silent, stellar diaspora. The true chaos would begin mere months before the end. The expansion of space within our solar system would become so ferocious that the sun's gravity could no longer hold onto its planets. Earth would be ripped from its orbit, a lonely wanderer in an increasingly fractured reality. In the final minutes, the forces that bind a planet together would be overwhelmed. The ground itself would tear apart. In the last few seconds, the very fabric of matter would disintegrate, atomic bonds would snap, nuclei would be torn from their electrons. And in the final, unimaginable instant, space-time itself would be shredded. The universe would end not with a whisper, but with a catastrophic tear in the fundamental canvas of reality. This apocalyptic vision hinges on the existence of a phantom field, a particularly exotic form of quintessence whose properties grow more extreme over time. While it remains a speculative and frightening possibility, it serves as a stark reminder of the sheer power we are dealing with, the fate of every atom, every force, and the continuum of space and time may ultimately rest on the precise value of a single, elusive number. Before dark energy entered the picture, the cosmos seemed destined for a dramatic and fiery finale known as the Big Crunch. This was the original grand finale, a cosmic bookend to the Big Bang where the universe's expansion would eventually halt, reverse, and send all of creation collapsing back in on itself. Galaxies would rush toward each other, the background temperature of space would soar, and the entire universe would ultimately be compressed into an ultra-hot, ultra-dense singularity, a mirror image of its birth. It was a compellingly symmetrical end, a universe that lived and died by gravity's pull. That entire narrative collapsed with the discovery of the accelerating expansion. The data points overwhelmingly away from a collapse and toward an eternal expansion. Yet, the Big Crunch is not completely dead. It lingers as a ghost of a possibility within certain models of dynamic dark energy. If the quintessence field were to decay, losing its repulsive power and perhaps even flipping to become an attractive force, the phantom's push could one day vanish. The brakes of gravity could re-engage, pulling the cosmos back from the brink of eternal expansion and onto a long, slow collapse. While highly speculative, this idea reminds us that the phantom's nature is not yet set in stone. Another profound alternative is the Big Bounce. This theory transforms a single crunch from an ending into a transition. Imagine our universe contracting down to that searing singularity, but instead of ending, it rebounds. A new Big Bang erupts from the ashes of the old cosmos, birthing a fresh universe with its own physical constants and laws. This suggests an eternal, cyclical cosmos, an endless rhythm of expansion and contraction where each universe is a chapter in an infinite story. The key to this cycle, once again, is dark energy. Its properties would determine whether a bounce is possible or if the collapse is truly final. Then there is perhaps the most unsettling end of all, one that could happen at any moment without warning. This is vacuum decay. Our universe may not be in its most stable state. The Higgs field, which gives particles their mass, might be sitting in a false vacuum, a metaphorical valley that seems stable but rests next to a much deeper, truer valley. A random quantum fluctuation could act as a trigger, creating a bubble of this true vacuum. This bubble would expand at the speed of light in all directions, rewriting the fundamental laws of physics as it goes. Within this bubble, the forces that hold atoms together would cease to exist as we know them. Everything, planets, stars, life itself, would be instantly and utterly erased, not by force, but by a change in the very rules of reality. The triggering of such an event depends on the precise energy landscape of these cosmic fields, a landscape whose shape is intimately tied to the same dark energy that drives our acceleration. All of these destinies, from the freeze to the rip, the crunch to the bounce, are scripts waiting to be chosen. The author holding the pen is the invisible, enigmatic force we call dark energy. Its unknown properties will write the final sentence of our universe's story. But what if the phantom is not real? What if dark energy is a grand illusion, a cosmic sleight of hand born from our own limited perspective. This provocative question is at the heart of a growing scientific controversy. Some physicists argue we are misreading the universe's expansion, and they propose radical alternatives that do away with dark energy entirely. One compelling idea suggests we live in a special place, not in the cosmic sense of importance, but in a literal, physical sense. Imagine our Milky Way galaxy sits at the center of a colossal cosmic void, a bubble of relative emptiness billions of light years across. In such an underdense region, the gravitational pull from the surrounding matter would be unbalanced. The denser regions outside our void would exert a stronger pull, effectively creating a gravitational gradient that makes it seem as though everything outside our local neighborhood is rushing away from us at an accelerating pace. It would be a local illusion projected onto a cosmic scale, like a boat drifting into a powerful current and mistaking the moving water for its own increasing speed. While this model can mimic cosmic acceleration, it faces a significant challenge. The cosmic microwave background, that pristine fossilized light from the Big Bang, reveals a universe that is remarkably uniform. For us to be in such a vast void, we would have to occupy a genuinely special and unlikely location, contradicting the cherished Copernican principle that we do not live in a privileged spot in the cosmos. An even more profound alternative seeks to rewrite the rules of gravity itself. For a century, Einstein's general relativity has reigned supreme, perfectly describing the cosmos from the orbit of Mercury to the bending of light around galaxies. But what if it breaks down on the very largest scales? Theories like modified Newtonian dynamics, or MUND, extended to cosmology, propose that our understanding of gravity is incomplete. One such theory, known as tensor vector scalar gravity, introduces new fields that alter how gravity behaves over immense distances. In these models, the observed acceleration isn't driven by a mysterious energy. It is a signature of gravity weakening differently over cosmic spans than general relativity predicts. The motion of galaxies and the dimming of supernovae become natural consequences of a revised law, no phantom required. So why does dark energy remain the favored explanation despite its profound mysteries? The answer lies in a principle scientists call parsimony, often known as Occam's razor. Between a mysterious, uniform energy permeating all of space and the need for a special, giant void or a fundamental rewrite of our most successful theory of gravity, the cosmological constant is ironically the simplest solution. It fits the data from supernova, the cosmic microwave background, and Barion acoustic oscillations with a single, elegant number. The modified gravity theories, while brilliant, often struggle to simultaneously explain all these independent observations without introducing their own complex new elements. This ongoing debate is not a sign of weakness in cosmology. It is the sound of a healthy, thriving science. The tension between a strange new energy and a modification of gravity is the engine of discovery, pushing observers to collect better data and theorists to sharpen their ideas. The phantom may yet be real, but the hunt for alternatives ensures we are not just telling ourselves a comfortable story. We are forcing the universe to reveal its true nature, one challenging controversy at a time. The deepest clues might be hidden in dimensions we cannot see. String theory, a bold and controversial framework for a theory of everything, attempts to unite gravity with quantum mechanics by proposing that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings. The different vibrations of these strings, much like the various notes on a guitar string, give rise to every particle and force we observe. To make the mathematics of this theory work, it requires more than the three spatial dimensions and one time dimension we experience. It demands extra dimensions, perhaps 6 or 7 of them, all curled up into a space so infinitesimally small that they are completely hidden from our view. The specific way these dimensions are folded and compactified, their shape and size, determines the effective laws of physics in our familiar 4-dimensional world, including the value of the cosmological constant. This is where string theory offers a potential, though speculative, solution to the cosmological constant problem. The theory does not predict one single universe, but a staggering multitude of possibilities, a landscape of perhaps 10 to the 500 different vacuum states. Each of these states corresponds to a universe with different physical constants, different forces, and a different value for dark energy. In the overwhelming majority of these universes, the cosmological constant is enormous, leading to instant dispersal or collapse. Our universe, with its peculiarly tiny positive value for dark energy, would be an incredibly rare oasis in a vast desert of cosmic possibilities. We exist not because the numbers are fine-tuned for life, but because life can only arise in one of the rare pockets where the numbers accidentally allow it. This is the anthropic principle applied to a cosmic scale. While this landscape of possibilities offers an explanation for why the vacuum energy is so small, it comes with a profound implication: the concept of a multiverse. If the string theory landscape is real, then our entire cosmos is just one bubble in an infinite froth of universes, each with its own unique laws. This idea is currently untestable, placing it at the frontier of theoretical physics. Yet it represents a monumental shift in thinking, suggesting that the phantom force tearing our cosmos apart may not be a fundamental mystery, but simply a local address in an infinite cosmic metropolis. This line of reasoning leads us directly to one of the most controversial ideas in modern science, the Anthropic Principle. It proposes a startling answer to the question of why dark energy is so inexplicably weak. Perhaps the constants of nature, including the density of dark energy, are not dictated by a fundamental law. They are simply the outcome of a cosmic lottery, and we are the lucky winners. In a multiverse of infinite possibilities, with every conceivable value for dark energy, we naturally find ourselves in one of the rare, habitable bubbles where the numbers just happen to be right. If the value of dark energy were even slightly larger, the repulsive force would have been so powerful that it would have blown the primordial gas clouds apart before they could ever coalesce into the first galaxies. No stars would have ignited, no planets would have formed. The universe would be a cold, thin, and eternal emptiness. Conversely, if dark energy were significantly weaker, or worse, negative, the gravitational pull of matter would have overwhelmed the expansion billions of years ago. The cosmos would have collapsed back in on itself in a fiery big crunch, long before complex life could ever emerge. We exist, therefore, in a very narrow window of possibility, a universe that appears exquisitely fine-tuned for our presence. For some scientists, this is a profound and necessary shift in perspective. It moves the question from why are the constants what they are, to why do we find ourselves in this particular universe with these specific constants. The answer becomes self-evident. We are here because this is one of the few places that could have produced us. For many other physicists, however, this feels like a philosophical surrender. They argue that invoking the anthropic principle is a conversation stopper, a way of giving up on the search for a deeper, more predictive physical law. It replaces the dream of a single, elegant theory of everything with a cosmic democracy of all possible worlds. The debate is not merely academic. It strikes at the very heart of what science is meant to do. Is our universe unique and fundamental, or is it just one page in an infinite library of realities? the phantom force of dark energy may be more than a cosmic mystery. It could be the first hard evidence that our entire cosmos is but one fragile bubble in a frothing multiverse. To solve this puzzle, we must build new eyes. The mystery of dark energy is now the driving force behind a new generation of astronomical observatories, each designed to trap the phantom in a web of irrefutable data. The European Space Agency's Euclid mission, launched in 2023, is a dedicated dark energy hunter. Its sole purpose is to map the invisible geometry of the dark universe with a clarity never before achieved. It will employ its two powerful techniques with surgical precision, measuring the subtle distortions of weak gravitational lensing across billions of galaxies and charting the cosmic web through galaxy clustering. This will create a three-dimensional map of both dark matter and the imprint of dark energy's push across cosmic time. Meanwhile, NASA's upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will take a broader and deeper look. It is designed to perform enormous ultra-deep surveys of the sky, acting as a supernova factory. It is expected to discover and analyze thousands of these stellar explosions, far more than the original teams could ever have dreamed of, building a supremely detailed history of the expansion rate. At the same time, it will measure the Barion acoustic oscillations, that frozen sound wave imprint, with such incredible precision that it will function as a golden ruler for the cosmos. But the view will not only come from space. From a mountaintop in Chile, the Vera C. Rubin Observatory will soon begin its legacy survey of space and time. This ground-based behemoth will not take a single snapshot of the universe. Instead, it will capture the cosmos in motion, repeatedly scanning the entire southern sky every few nights for a decade. This will create the most ambitious astronomical movie ever made, a dynamic, living portrait of the sky that will reveal subtle changes and track the motions of billions of celestial objects. The collective goal of these missions is razor-sharp, to measure the equation of state parameter W with a precision of 1% or better. This is not a minor improvement. It is the difference between seeing a silhouette and recognizing a face. Such accuracy could finally rule out entire classes of theories, potentially killing the simple cosmological constant or sending physicists scrambling to explain a deviation from -1. The data flood is coming, a torrent of information that will either confirm our darkest cosmic fears or reveal a universe even stranger than we ever imagined. The very force that isolates galaxies may also be spawning entire realities. This profound connection between dark energy and the multiverse hinges on a theory called eternal inflation. Imagine the primordial cosmos not as a single exploding point, but as an endlessly inflating substrate, a meta-universe constantly giving birth to new pocket universes like bubbles in a vast, boiling cauldron. Each of these bubbles nucleates with its own random set of physical laws and constants. The value of dark energy within our universe, that strangely small number that allows for galaxies and life, is not a fundamental law. It is simply a local condition, a lucky draw in an infinite cosmic lottery. In this breathtaking view, dark energy acts as the interior architect for each bubble universe, setting the stage for its ultimate fate. A slightly stronger dark energy would have blown our universe apart before any structure could form. A weaker value would have caused a swift collapse. Our existence here is a direct consequence of this specific, gentle acceleration. But the influence of this phantom force does not stop at creation. Our own accelerating cosmos is actively generating new universes in a different, more haunting way. As the repulsive push of dark energy intensifies, vast regions of space are being pushed beyond our cosmic horizon, moving away faster than light can ever connect us. These regions become causally disconnected islands, their futures forever separate from our own. In a very real sense, dark energy is taking our one observable universe and shearing it into an endless number of isolated patches. Each patch, no longer able to interact or communicate with the others, evolves on its own trajectory, effectively becoming a separate universe with its own history. The phantom is not just tearing our cosmos apart, it is the engine of infinite genesis, simultaneously determining the properties of our local reality, while ensuring that countless others will always remain just out of reach, a silent, expanding ocean of untold cosmic stories. Our cosmic narrative has been fundamentally rewritten, and the new story has no special role for us. The dominant force in the universe is not gravity, the builder of galaxies and stars, but a repulsive phantom that systematically dismantles cosmic structure over time. We find ourselves living in a fleeting window of cosmic opportunity, a brief golden era nestled between the primordial fireball and an approaching eternity of cold emptiness. For billions of years, gravity had the upper hand, allowing the first stars to ignite and galaxies to assemble. For a few billion more, the conditions will remain just right for life to exist. But this is a temporary state, a cosmic spring that will inevitably give way to a deep and permanent winter. This perspective is profoundly humbling. It shatters the last vestiges of an anthropocentric universe, the comforting idea that the cosmos was somehow designed with us in mind. Instead, we are confronted with a reality governed by vast, impersonal forces that are utterly indifferent to our existence. The universe is not hostile, nor is it friendly. It is simply there, following its own inscrutable rules, with dark energy as its silent, relentless engine. This realization can feel like a form of cosmic loneliness, but it can also be strangely liberating. If the universe is not made for us, then our meaning is not handed to us from the cosmos. We are free to create it for ourselves. Every achievement, every work of art, every act of compassion gains a new and poignant significance against this dark, accelerating backdrop. They are not part of a grand, preordained cosmic plan. They are our own fragile lights, kindled in the brief twilight between two immense and uncaring darknesses. The phantom force tearing the cosmos apart forces us to ask the most fundamental question of all. What does it mean to be human in a universe that is ultimately transient? A universe whose final chapter is already being written by an invisible, alien energy we may never fully understand. The equations of cosmology have begun to leak into our cinemas and bookshelves. Dark energy, the phantom force of physics, has been reborn in popular culture as a wellspring of cosmic power and dread. Science fiction authors and filmmakers, unburdened by the strictures of peer review, have seized upon its mysterious nature to fuel narratives of grand adventure and existential terror. In many stories, it is reimagined as a tangible resource, an exotic particle or field that can be harnessed for impossible technologies. Vessels ride waves of dark energy to cross interstellar distances in the blink of an eye, treating the cosmos's expansion as a current to be sailed. In other tales, it becomes the ultimate weapon, a device that can locally amplify this repulsive force to tear enemy fleets or entire worlds apart at the subatomic level. These depictions are, of course, wildly speculative. Real dark energy is not a substance you can bottle or a force you can aim. It is a uniform, subtle property of space itself, utterly indifferent to our desires. Yet the inaccuracy is beside the point. These fictional interpretations act as a cultural barometer, measuring our collective awe and anxiety in the face of this discovery. They transform an abstract cosmological parameter into a story we can feel. the sheer scale of the real phenomenon, a force that dictates the fate of the entire universe, demands a mythical response. We give it a face, a purpose, and a name, turning the equations into dragons and magic fuels because our minds are built for narrative, not for lambda cold dark matter models. This process of myth-making is not new. Every great scientific mystery, from the atom to the black hole, has undergone a similar transformation in the public imagination. These stories are a testament to the power of the human mind to look into the abyss of the unknown and not only seek data, but to craft a legend. They are the first, faltering translations of a cosmic truth we do not yet fully understand, a signal that the phantom has escaped the lab and now haunts our dreams. These cosmic mysteries feel impossibly large, yet we can hold them in our minds through the power of a simple analogy. The most enduring model for the expanding universe is a loaf of raisin bread baking in an oven. In this cosmic kitchen, the dough itself represents the fabric of space-time. The raisins are galaxies. As the dough rises, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are receding, and the farther away a raisin is, the faster it seems to retreat. This beautifully illustrates the basic expansion discovered by Edwin Hubble. Now introduce dark energy. Imagine the yeast in that dough suddenly, billions of years into the bake, becomes supercharged. It doesn't just continue making the bread rise, it makes the dough expand at an ever-increasing rate. The raisins don't just move apart, they fly away from each other faster and faster, stretching the distances between them with a frantic, growing urgency. This is the essence of accelerating expansion. Another powerful image is the inflating balloon. Picture the surface of a balloon with coins glued to it, each coin a galaxy. As you blow air into the balloon, every coin moves away from every other coin on that two-dimensional surface. Now, imagine you start blowing with increasing force, pumping more and more air in with each breath. The balloon's surface doesn't just grow, it stretches faster and faster, forcing the coins apart at an accelerating pace. The person blowing, supplying that relentless, increasing push, is the dark energy. These analogies are invaluable, but they all have their limits. The balloon, for instance, suggests the universe is expanding into something which may not be true. The raisin bread implies a center, a specific raisin from which everything is moving away, when in reality, every point in the cosmos sees itself as the center of the expansion. The true nature of dark energy is not a substance being added like air into a balloon, but a property of the dough or the balloon's rubber itself changing, generating a repulsive gravity from within. Despite their flaws, these imperfect pictures are our first, crucial step. They translate an abstract equation into a story we can feel, giving our intuition a foothold in a reality that is fundamentally stranger than fiction. The phantom force shaping our future may have a twin from the distant past. In the very first sliver of a second after the Big Bang, the cosmos is thought to have undergone its own incredible growth spurt, a period known as cosmic inflation. This was not the steady, stately expansion we see today. It was an explosive, exponential stretching, doubling the size of the universe again and again in intervals far shorter than a blink. The hypothetical engine behind this primordial frenzy is called the inflaton field. Like dark energy, this field possessed a peculiar property, a powerful negative pressure that generated a form of repulsive gravity, pushing space itself apart with unimaginable force. For a fleeting moment, the inflaton field dominated the cosmos, smoothing it out and seeding the structures that would become galaxies. Then, just as suddenly, it decayed, its energy transforming into the hot soup of particles that would forge the first atoms. Now, billions of years later, a different form of energy, dark energy, has taken up the mantle of cosmic expansion. The parallels are striking. Both are driven by fields with negative pressure, and both cause the fabric of space-time to stretch. Yet the differences are just as profound. Cosmic inflation was unimaginably violent and brief, a sprint that lasted perhaps a millionth of a billionth of a billionth of a second. Dark energy, by contrast, is a cosmic marathon runner, exerting a vastly weaker but persistent push over billions of years. One field ignited the universe's birth, while the other may dictate its long-term fate. Could they be different faces of the same fundamental phenomenon? Perhaps the inflattened field did not completely vanish but left behind a faint remnant, a ghost in the machinery that we now detect as dark energy. Or maybe our universe contains a family of such fields, each awakening at different epochs to steer cosmic evolution. The search for a unified theory that can describe both the beginning and the end with the same mathematics is one of the most ambitious quests in physics. It suggests that the first instant of creation and the final destiny of all things are woven together by the same mysterious, invisible threads. Decades of investigation have brought us face to face with the phantom, yet its true nature remains more elusive than ever. Our most profound discovery is the sheer depth of our own ignorance, and the questions that remain are the very forces driving cosmology forward. The most fundamental of these is the simplest to ask and the hardest to answer. What is dark energy? Is it the static hum of empty space, Einstein's cosmological constant, or is it a dynamic, changing field like Quintessence? Our entire vision of the cosmic future, from a gradual freeze to a violent rip, hinges on this distinction. We have a number that fits the data, but we have no idea what that number represents. This leads directly to the second great puzzle, the cosmological constant problem. Why is the measured energy density of the vacuum so unimaginably small? The theoretical prediction from quantum physics overshoots reality by a factor of 1 followed by 120 zeros. This is not a small error. It is the most glaring discrepancy in all of science, a screaming clue that our understanding of the universe's most basic fabric is fundamentally broken. Does dark energy exist in total isolation, or could it secretly interact with the other great mystery, dark matter? We know these two phantoms together make up 95% of the cosmos, yet we model them as completely separate entities. What if they talk to each other? A subtle interaction could explain why dark energy became dominant exactly when it did, a cosmic coincidence that has always troubled physicists. Then there is the most radical question of all. Are we even on the right track? Is dark energy real, or is it a grand illusion, a sign that Einstein's theory of gravity, while brilliant, fails on the largest scales of the universe? Perhaps the acceleration is not a force but a signal, telling us that our laws of physics are incomplete and need a fundamental rewrite. Each of these open questions is a frontier. They are not dead ends but pathways, invitations to a deeper reality. The mystery of dark energy is not a wall that blocks our progress. It is an engine powering the telescopes, the space missions, and the brilliant minds dedicated to reading the final chapters of our universe's story before they are written. This invisible quest is reshaping the technology we use every day. The monumental effort to map the dark universe has demanded tools that did not exist just a generation ago, forcing a wave of innovation that ripples far beyond the observatory. To capture the light of billions of galaxies, engineers had to design cameras of almost unimaginable scale and sensitivity. These are not ordinary digital cameras. They are behemoths like the 3.2 billion pixel sensor built for the Vera C. Rubin Observatory, a device so powerful it would take over 1,500 high-definition television screens to display just one of its full-resolution images. At the heart of these instruments are charge-coupled devices, or CCDs, perfected for astronomy. These ultra-sensitive chips can detect the faintest whisper of light from the edge of the observable universe, but their precision also makes them invaluable in medical imaging, where they improve the resolution of X-rays and cancer screening technologies. Yet capturing the light is only the first challenge. A single night of observation can produce enough data to fill a stack of laptops stretching to the ceiling. This deluge of cosmic information has birthed entirely new fields of data science. Astronomers, collaborating with computer scientists, have developed sophisticated machine learning algorithms to automatically identify galaxies, classify star types, and find subtle patterns in the noise that no human eye could ever see. These same algorithms are now being adapted to diagnose diseases from medical scans, predict extreme weather patterns by analyzing global climate data, and train artificial intelligence to solve complex logistical problems. The search for a phantom in the void has become a powerful engine for computational advancement, proving that the tools we build to answer our biggest questions often end up transforming the world right in front of us. The alarm goes off at 4 in the morning, not for a sunrise, but for a sunset on the other side of the world. A cosmologist's day often begins in a control room perched on a remote mountain, the air thin and cold outside. She is not peering through an eyepiece but staring at a bank of monitors, her fingers flying across a keyboard. Her telescope time, a precious few nights awarded after a highly competitive proposal, is ticking away. Every second of clear, dark sky is a treasure. She monitors the weather, checks the focus of the massive mirror, and queues up a list of distant galaxy coordinates for the instrument to observe. The work is a strange mix of the profoundly cosmic and the mundanely technical. A single loose cable or a patch of high-altitude haze can ruin hours of data collection. This is the reality of the hunt, a patient, meticulous dance with a universe that does not care about your deadlines. Back in a university office months later, the real detective work begins. The raw data from the telescope is a chaotic symphony of signals, filled with the hiss of cosmic rays and the glare of stray light from our own planet. Her tools are not telescopes now, but algorithms. She spends weeks writing and rewriting code, creating digital filters to clean the noise and isolate the pure, faint light from galaxies billions of light years away. She models the subtle distortions of weak gravitational lensing, simulating how dark matter bends the path of that ancient light. Each line of code is a question posed to the universe. The answers come not in a flash of insight, but in the slow, grinding progress of debugging errors and validating results against known standards. Frustration is a constant companion, a nagging doubt that a tiny, overlooked systematic error could invalidate an entire year's work. Then the moment arrives, a new dataset from a space telescope like Euclid or Roman is released to the collaboration. For a day, the routine of coding and analysis stops. The office is filled with a palpable buzz of excitement as colleagues crowd around a screen. They are seeing a patch of the universe mapped with a clarity no human has ever witnessed before. The filaments of the cosmic web, traced by millions of galaxies, appear in stunning detail. In that raw data dump, they might find the one anomalous measurement, the slight but persistent deviation in the clustering of galaxies that could hint at a dynamic dark energy. It is a spark, a reminder of the profound mystery that drew them to this work in the first place. The final stage is perhaps the most human of all, collaboration on a scale that would have been impossible a generation ago. A single research paper detailing their findings might have hundreds of co-authors from dozens of countries. For weeks, they debate over shared documents and video calls, arguing over the interpretation of a statistical fluctuation, the wording of a critical sentence, the confidence level of their conclusion. It is a slow, deliberate process of consensus building, a collective effort to ensure their result is robust enough to withstand the scrutiny of the entire scientific community. The grand quest to understand the phantom force shaping our cosmos is built on these countless ordinary days, a testament to human curiosity and the relentless, patient pursuit of a truth that forever lies just beyond our grasp. Behind the walls of major observatories, a quiet revolution is reshaping how we explore the cosmos. The sheer volume of data from dark energy surveys is so immense that even the most powerful supercomputers and the largest research teams cannot process it all alone. A single sky survey can capture images of billions of galaxies, each one needing to be examined and classified by a discerning eye. This is where the global community steps in, transforming everyday curiosity into a powerful scientific instrument. Projects like Galaxy Zoo invite anyone with an internet connection to become a cosmic cartographer. You might log on and be presented with a stunning, never-before-seen image of a distant galaxy. Your task is simple yet profound: to answer a few basic questions. Is it a smooth, fuzzy ellipse? Does it have majestic, winding arms? Or is it a chaotic mess, perhaps the result of a galactic collision? This act of pattern recognition, something the human brain excels at, is incredibly difficult for even the most advanced algorithms. A computer might struggle to distinguish a spiral galaxy's delicate arms from a streak of cosmic dust, but a person can do it in an instant. With hundreds of thousands of volunteers making these classifications, the collective power is staggering. The data is processed at an unprecedented rate, revealing the large-scale structure of the universe with a clarity that would otherwise take years to achieve. This is not busy work. Galaxy Zoo participants have made genuine discoveries, stumbling upon entirely new classes of astronomical objects. They have found rare green P-galaxies, which are hotbeds of star formation, and they have identified peculiar galaxies that have led to published scientific papers. Every click, every classification, is a small but vital contribution to the great map we are building. It is a map that traces the distribution of both visible matter and the invisible dark matter that shapes it, a map whose evolving patterns hold subtle clues about the repulsive push of dark energy. This process does more than just accelerate research. It forges a deep, personal connection between people and the universe. You are no longer just a passive observer of science headlines. You are an active participant in the greatest detective story of all time, helping to sift through the evidence left behind by the phantom force. It democratizes discovery, proving that the quest to understand dark energy is not confined to a small group of experts on a mountaintop. It is a human endeavor, a shared journey into the unknown that anyone can join, turning a moment of wonder into a tangible piece of the cosmic puzzle. This accelerating expansion builds an invisible wall at the edge of our perception. Dark energy is actively constructing a cosmic event horizon, a point of no return for information. Light emitted from galaxies beyond this horizon is trying to swim against a current of space that is stretching faster than the speed of light itself. The photons are like a runner on an accelerating treadmill, expending all their energy but making no forward progress, forever stranded in the expanding void between us and them. As a result, we are being permanently cut off from a vast portion of the cosmos. This horizon is not static. It is slowly but surely closing in on us, not in space but in time. More and more galaxies are crossing this threshold every moment, their final signals reaching us as a last, fading whisper before they vanish from our view for all eternity. Future astronomers looking up at the sky billions of years from now will witness a profoundly impoverished universe, the grand tapestry of the cosmic web. The evidence of billions of galaxies will have receded into an impenetrable blackness. They will have no way of knowing what lies beyond, or that a rich and structured cosmos ever existed. This creates a permanent and shrinking ceiling on the observable universe. A vast archive of cosmic history, the tales of countless galactic civilizations and stellar evolutions, will become fundamentally unknowable. Dark energy is not merely dictating our future. It is systematically erasing our past, placing a final, absolute limit on the grand story we will ever be able to tell about our home in the cosmos. This invisible force shaping our cosmic destiny might also hold the key to a profound earthly mystery, the silence of the cosmos. The same dark energy that dictates our universe's ultimate fate could be a decisive factor in the scarcity of intelligent life. Consider the delicate timeline required for our own existence. It took nearly 10 billion years for the first stars to form, forge heavy elements in their cores, and explode, scattering the ingredients for planets and life across the galaxy. It took another 5 billion years for our solar system to coalesce and for intelligent life to finally emerge on Earth. If the value of dark energy had been only slightly stronger, accelerating the expansion with a more violent urgency, the universe would have been torn apart before this intricate chain of events could even begin. Galaxies would have been shredded in their infancy, stars flung into the void before planetary systems could stabilize. Conversely, a slightly weaker dark energy would have allowed gravity to win, pulling the cosmos back into a fiery big crunch billions of years ago, cutting the story short. The specific, curiously small value we observe creates a golden window, long and stable enough for evolution to run its slow, miraculous course. This precise tuning places dark energy at the heart of a chilling idea known as the Great Filter. This hypothesis suggests that there is some enormous, nearly insurmountable barrier that prevents life from progressing to the stage of building a visible, galaxy-spanning civilization. Perhaps the filter is not behind us in our own past, but ahead of us, written into the fundamental laws of physics. The value of dark energy might be that filter. It could be that in the vast majority of universes, the cosmic conditions are either too violent or too brief for intelligence to ever get a foothold. We do not see other civilizations because in a cosmos with different rules, they never could have arisen. Yet there is another, more hopeful possibility. What if a species does manage to reach a point where it understands the phantom force accelerating the universe? A civilization that advanced would have moved beyond merely observing the stars to potentially manipulating the very fabric of spacetime. Could they learn to harness dark energy itself? The ability to control this repulsive force would be the ultimate technological achievement, a power source of literally cosmic proportions or a means of propulsion that could defy the expansion of space. If such beings exist, their signature might not be radio signals but something far stranger, a subtle, engineered anomaly in the acceleration of the universe itself, a fingerprint on the cosmos's final chapter. The search for extraterrestrial intelligence may not just be about listening for a message. It might be about reading the fine print in the universe's expansion history, looking for signs that someone else has already learned to speak the language of the void. Our journey through the phantom force ends not with an answer but with a transformed reality. We began with a single number Einstein called his greatest blunder, a mathematical fudge that turned out to be a prophecy. We followed the trail of dying stars, the ancient whisper of the cosmic microwave background, and the frozen echoes of primordial sound, each piece of evidence converging on the same astonishing truth. An invisible energy making up the overwhelming majority of everything is relentlessly stretching the fabric of the cosmos, pushing it toward a future of profound isolation or catastrophic disintegration. This is not a niche curiosity. It is the central plot of our universe's story, a force that overrules the gravity which built the galaxies and stars we call home. The mystery of dark energy now stands as a monumental challenge, a fault line running through our most successful theories. It pits the cosmic scale of general relativity against the frantic quantum world, revealing a fundamental incompatibility in our understanding of reality itself. This is not a small gap in knowledge. It is a chasm, and building a bridge across it requires the most ambitious scientific instruments ever conceived, from space telescopes mapping the dark universe to ground-based observatories making a decade-long movie of the sky. This quest does more than just advance physics. It redefines our cosmic address. We have learned that the atoms we are made of are a rare and exotic contaminant in a universe dominated by two invisible phantoms, dark matter and dark energy. We are not the center of the cosmos, nor are we even made of its primary ingredients. We exist in a fleeting, golden era between two immense darknesses, a brief window where the universe is just calm and structured enough for life to spark. And in that realization lies a profound liberation. The universe is not for us, but we are of it. Our meaning is not written in the stars, it is written by us. Every act of curiosity, every discovery, every moment of connection gains a new and poignant significance against this dark, accelerating backdrop. The invisible power tearing the cosmos apart is also, paradoxically, the very thing pulling us toward a deeper, more humble, and more wondrous understanding of our place within the infinite.